Thank you. Rudy Ahlswede for me will always be a special person for many reasons, two of which are the following. He was a giant in information theory and in combinatorics and in mathematics in general, whose ideas had a very important influence on the work of others, including me. And secondly, since I first met him in 1988 in Leuven at a workshop organized by Ed van der Meulen, he's always taken a personal and very friendly interest in my career, and he helped me in many cases. The last time I saw him was about 4 or 5 years ago when he was visiting Boston University, and he came down to the University of Maryland where I work, and he spent 4 or 5 days there, and he simply charmed everybody, students, faculty, staff, everybody. That was the last time I saw Rudy. This talk deals with common randomness and multi-terminal secure computation, in particular with secret common randomness, of which Imre just spoke. It's joint work with Himanshu Tyagi, who is my PhD student at the University of Maryland, and with Piyush Gupta, who is at Bell Labs Alcatel-Lucent. And the problem, very loosely stated, is the following. There are M terminals in the multi-terminal source model to which Imre referred. M terminals, they all observe signals, and these signals in general are correlated with each other. And these terminals are required to compute a given function of all these signals. And in order to do that, they exchange information among themselves over a channel which is public. And an eavesdropper gets to see the bits that are going across this public channel. And the objective is to compute the value of the function. The legitimate terminals, the M terminals, must compute the value of the function without giving away the value of the function to the eavesdropper that has observed this public communication. And the question we ask is this possible in general for a given function, and what are conditions under which this can be done? So to formulate the model, this is the multi-terminal source model, which Imre and I considered in a different context of secret key generation, which will come to play a role in this problem as well. There are M terminals numbered 1 through M, and they observe signals. To describe these signals, well, first, there are M legitimate terminals, and the set of terminals will be denoted by script M. And these M signals observe correlated signals. And in order to describe these correlated signals, there are M random variables, x1 through xm, one corresponding to each terminal. And these random variables are assumed to take values in finite alphabets, and they have a known joint distribution. Each terminal I, running from 1 through m, is going to observe a signal which consists of n IID independent and identically distributed repetitions, let's say in time, of the random variable x sub I. Therefore, terminal I observes the sequence xi1 through xin, where the first subscript refers to the index of the terminal and the second subscript refers to the index in time of the observed symbol. And the abbreviation we'll use is x sub I sup n. The subscript again refers to the index of the terminal, and the superscript refers to the length of the observed sequence. Now, we'll allow randomization at the terminals, 1 through m, and this randomization is modeled by m random variables u1 through um, which are taken to be mutually independent and independent of all these signals observed by all the terminals. Now, continuing with the description of the model, all these terminals are allowed to communicate among themselves, and they do so over a public noiseless channel of unlimited capacity. Possibly interactively, the communication can be interactive and can take place in multiple rounds. The communication from any single terminal is observed by all the other terminals, which means that the communication takes place in a broadcast mode. The communication from any terminal I is allowed to be any function of its own observed signal xin. It's allowed randomization ui, and of all the previous communication that has taken place over the communication channel. Throughout this talk, we are going to denote by F collectively all the public communication among all the terminals. Now, the secure computing problem in which we are interested is the following. I'm going to denote by X subscript M, the product alphabet of all the product of all the alphabets in which the random variables take their values. And the function to be computed is going to be defined in terms of a mapping G, which is a single letter mapping. G is a mapping from the product alphabet to some finite set Y. Okay, so for every symbol, G acts on the symbols. For every point, at every point in time, G acts on the symbols observed by all the terminals. So that gives us G. But since the sequences have length n, the mapping Gn, which acts on all the signals, is a mapping from xmn to yn. And as I said, it's a single letter function, so Gn acting on all the signals from all the terminals of length n is going to have n components, with G acting on the first symbols observed by all the terminals at all the time instants, and so on until the nth time instant. I'm going to denote the random variable Gn of all the signals by capital Gn for every value of n, except for n equal to 1, where I'll simply call it G. So G is simply the random variable G of xn. Examples of such functions are symbol-wise parity, average, maximum, minimum, etc. And the overall objective is the following. The terminals in the set of terminals wish to compute the function Gn securely using public communication F in such a way that the public communication does not give away the value of the function to an eavesdropper who observes the public communication. Pictorially, this is how secure computing is defined in a precise way. So there are M terminals. They observe, each of them observes a corresponding signal. U1 through UM is the allowed randomization at each terminal. F denotes the public communication among the terminals. And each terminal I constructs an estimate of the function Gn based on its own locally observed signal xin, its local randomization ui, and of all the public communication. And we require that each of these M local estimates agree with the true value of the function, with probability approaching 1 as the signal length n approaches infinity. That's the computability condition. So a function f is securely computable if it satisfies the computability condition. And secondly, it satisfies what is called the strong secrecy condition, which says that the value of the function should be nearly independent or nearly independent of the observations of the eavesdropper, which means that the mutual information between Gn and f must approach 0 as n approaches infinity. So these are the two conditions. And the question we ask is a very elemental question. Given a function g, when can a function g be computed so that its value is independent of the public communication that was used in its computation? Now, there is a significant body of related work, some of which is listed here. This is not a complete list. So there's a series of papers on, there are a series of papers on exact function computation without secrecy, then exact function computation with secrecy by Alon Orlitsky, who's here, and Abbas El-Gamal. And in fact, I mentioned this because the work that I'm going to describe is closest in spirit to the work of Alona and Abbas. Then there's information theoretic function computation without secrecy, information theoretic oblivious transfer. The question we ask is a little different from what has been sought in these works. We simply ask the question, when is a given function g securely computable? So we are not asking for the minimum rate of public communication which will enable the secure computation of g. This problem remains open even in the absence of secrecy constraints. Nor do we ask for efficient protocols for secure computation. Instead, we merely ask for necessary and sufficient conditions that must be satisfied to guarantee the existence of such a computation of such a protocol for secure computation. Now, the problem of secure computing is related to the problem of secret common randomness that Imre just spoke about. So in this work with Imre on secret key generation with public communication, so here's a pictorial representation of that problem. Once again, the setup is the same. There are M terminals, 1 through M. They are legitimate terminals. Each terminal observes a signal, each terminal I observes a signal xin. The signals are correlated with a given joint distribution. The terminals are allowed to randomize U1 through UM, and they are allowed to communicate over a public channel of unlimited capacity in multiple rounds. And the objective here is for each of these terminals to generate a random variable k, which is going to constitute a secret key. So k is a secret key for the terminals 1 through m. If at each terminal I, the terminal generates a random variable ki, which is a function of its own locally observed signal, xin, its randomization ui, and of the public communication f. And all these locally generated random variables must agree with k with probability approaching 1. So random variable k is a secret key for the terminals in M, achievable with public communication F. That is, it constitutes secret common randomness if it satisfies these two conditions. The first one is the condition of common randomness that I just described. And the second is the condition of strong secrecy, which says that the key must be nearly independent or independent of the observations of an adversary. And the secret key capacity, C of M, is the largest entropy rate of such a secret key for M, which can be attained with suitable communication. So it's simply the maximum rate of secret common randomness. Now, this problem, the problem of secure computation, is related to the problem of maximal rate secret key generation. And the reason is the following. So if we look at the picture here, you see if the random variable, if the terminals 1 through m can compute the function g securely, then by the definition of secure computability, these two conditions here, the computability and the secrecy condition, and a comparison with the definition of a secret key here, we see that a securely computed function must constitute a secret key or secret common randomness. Therefore, if a function g is securely computable by the terminals in M, then Gn constitutes a secret key for the terminals in M, which means, therefore, a necessary condition for secure computability is that the entropy of G be no larger than the secret key capacity for this model. Now, surprisingly, it turns out that this condition is also sufficient. And that is the main result of this talk, which is a characterization of secure computability. So a given function G is securely computable by the terminals in M if its entropy is strictly smaller than the secret key capacity for the model. And conversely, as we just saw, if G is securely computable, then its entropy clearly must not exceed the secret key capacity. And furthermore, under this sufficient condition here, G can be computed securely with non-interactive communication. So although interactive communication is allowed, it is not needed. A single autonomous transmission from each terminal is sufficient for the secure computability of G. Randomization need not be used. And furthermore, the secrecy condition is satisfied with this mutual information between the value of the function and the public communication going to 0 exponentially rapidly in N. So there are two things to complete here. So first is to give a formula for the secret key capacity so that this provides a condition that can be checked to see whether a given function is securely computable or not. And Imre just gave a formula for C of M. Secondly, we have to give a proof, or at least the outline of a proof, for this condition of sufficiency. So that's what we're going to do next. So let me start by going first to a formula for the secret key capacity. Recall that this is the problem of secret key generation. Such a key, as Imre said, can be used for secure encrypted communication. And the task is to write an expression for the secret key capacity. And that, as you just saw, is given by this expression. The secret key capacity is equal to the joint entropy of all the random variables in the model, x1 through xm. We subtract from it the smallest achievable aggregate rate, sum rate, which is RCO of M. So the notation is a little different from Imre's notation. Smallest achievable aggregate rate of communication, which enables all the terminals to become omniscient, that is, to reconstruct all the signals observed by all the terminals. And this is a joint entropy minus this minimum sum rate, where the sum of these numbers R1 through Rm must lie in a constraint set which looks like a Slepian-Wolf constraint set. So, and the secret key capacity has this expression. This is the formula that can be computed, and the secret key capacity can indeed be achieved with non-interactive communication. So a remark here is that in order to characterize the secret key capacity, of course, it's sufficient to characterize this minimum sum rate, which is needed for all the terminals to become omniscient. And that is the solution to a multi-terminal data compression problem of omniscience or common randomness generation that does not involve any secrecy constraints. Now, an interpretation of this secret key capacity result or formula is the following. All the M terminals cooperate through their public communication so as to enable themselves to become omniscient. So in other words, all the terminals communicate among themselves so that they can learn each other's signals. And this is done through public communication. Then once this, in the most efficient way possible, by using the minimum rate of such public communication, then all the terminals in M extract from their omniscience a secret key by purging away the rate of this public communication because it's been seen by the eavesdropper anyway. So that's the idea here. I won't get into the idea of the proof, but I thought before I give you an outline of the proof of sufficiency of the condition for secure computability, we'd look at a simple example with just two terminals to see how secure computation can be effected. So here there are two terminals, 1 and 2. They observe IID repetitions of the random variables x1 and x2. x1 and x2 are binary valued. Joint distribution of x1 and x2 is depicted by this picture. x1 is Bernoulli with the probability of x1 being 1 being equal to p, where p is some number between 0 and 1. The conditional distribution of x2 given x1 is depicted by this virtual binary symmetric channel with crossover probability delta, where delta is taken to be less than half. The given function that needs to be computed, g of x1, x2, is simply the modulo 2 sum of x1 and x2, namely the parity of x1, x2. And it's clear from here that the entropy of g is simply the binary entropy of delta. And that has to be compared with the secret key capacity for this model to see whether it's securely computable or not. That secret key capacity is simply the mutual information between x1 and x2, comes from the results of Maurer and Ahlswede and Chisar, and that is given by the difference between these two binary entropy functions. So therefore, by the result, G is securely computable if the entropy of G, namely the binary entropy of delta, is less than the mutual information between x1 and x2. Now, let's look at the special case where p equal to half. So x1 is uniformly distributed, therefore x2 is also uniformly distributed. In this case, the condition for secure computability becomes that the entropy of delta be less than the mutual information 1 minus h of delta, which means the entropy of delta must be less than 0.5. Now here's a scheme for the secure computability of G in this instance. And the idea uses Slepian-Wolf data compression, and the scheme is as follows. There are two terminals. Terminal 1 is going to send the Slepian-Wolf code, its Slepian-Wolf code word to terminal 2 with the signal at terminal 2 as side information. Then terminal 2 therefore reconstructs the signal at terminal 1. Since it knows both the signals, it's going to compute the parity that is desired. And then it's going to send the parity value back to terminal 1 with suitable encryption. And that's what's going to happen. So let's start by seeing how to do this. Because x1 and x2 are connected by virtual binary symmetric channel, let's look at a good capacity achieving channel code for this binary symmetric channel, and let P be its parity check matrix. Now here's a scheme suggested by Aaron Weiner in 1979 for the Slepian-Wolf data compression of the signal x1n to be received at terminal 2 with side information x2n. Now, so terminal 1 is going to send to terminal 2, as shown in this picture, a first communication f1, which is simply p multiplying its signal. So this is simply it sends the syndrome of its observed signal to terminal 2. Now here, Gn, which is the parity, is of course clearly independent of either of the two signals, so it's independent of x1n, and therefore it means that Gn is also independent of this communication from terminal 1 to terminal 2. Now, as a consequence of this, terminal 2 can reconstruct the signal at terminal 1 with large probability, and therefore it compute its value of the parity of the signal. Now, in the next step, terminal 2 is going to encrypt its estimated value of Gn and send it to terminal 1, and it does so as follows. So here's a secret key. Both terminals 1 and terminal 2 generate a secret key. That secret key K is simply the location of the signal of terminal 1 in the coset of the standard array corresponding to the parity check matrix P. So this standard array contains all the binary sequences of length n, and the signal observed at terminal 1 must be in one of the cosets, and the key is simply the location of x1n in the coset that contains it. The rate of this key is 1 minus h of delta, and this key is generated in such a way that it's independent of the communication that was used in its generation. So this mutual information is exactly equal to 0. And then it can be shown that the mutual information between the key and F1 and Gn is also 0. It's a straightforward computation. Now, what does terminal 2 do? Both the terminals know the key. Terminal 2 has computed the value of the signal. And here's where the secure computability condition comes in, that the entropy of G is less than the entropy of the key, which means that the length in bits of the parity Gn is smaller than the length of the key. And therefore, terminal 2 can encrypt its computed value of the function, and can encrypt it using a one-time pad and send it to terminal 1. And it can do this encryption because the length of Gn is smaller than the length of the key. Now, as a consequence, terminal 1, which also knows the value of the key, can reconstruct Gn. So both the terminals have now computed Gn. It remains to show that this computation was secure, which is equivalent to showing that the value of the function be independent of the total communication F1 and F2, and this again can be done by simple computation. So here's a simple instance of how the function, the parity, can be computed securely. Now, coming to the idea of the proof of sufficiency of this condition, the main idea is the following. The proof consists of showing the existence of non-interactive source code. This is a public communication, which has the following property. This public communication, or these source codes from the various terminals, will enable all the terminals in M to become omniscient, and these non-interactive source codes are such that they are simultaneously independent of Gn. So in other words, the proof consists of showing the existence of public communication, which enables all the terminals to become omniscient, and this communication is such that it is independent of the value of the function Gn to be computed. Since all the terminals become omniscient, they can clearly compute the function value Gn, and the communication that was used for the purpose is already known to be independent of Gn. And this can be done because of the sufficient condition that the entropy of G is no bigger than the secret key capacity. Pictorially, this is how things look. If you look at this model, here is 0. Here is the total joint entropy of all the random variables. Now, this total common randomness can be broken into two parts. The first is RCO of M, which is the minimum rate of communication for the terminals to become omniscient. And the second part is the secret key capacity, which is the largest rate of secret common randomness. And the random variables associated with these two parts are independent or nearly independent of each other. Okay. Now, if the entropy of G is strictly smaller than the secret key capacity, then the terminals in M can still communicate so as to contain omniscience, and the rate and the public communication that is used for omniscience is still independent of all the random variables in this part. In particular, the communication is independent of the value of the function of the random variable G. If the entropy of G is larger than the secret key capacity, then the communication here will not be independent of G. So that's the idea. Here are the main steps of the proof. I'll be very brief here. The entropy of the function being less than the secret key capacity means that the conditional entropy of the random variables x1 through xm conditioned on G is bigger than the minimum rate of communication for omniscience. The idea of the proof is to select random mappings Fi at each terminal I of rate Ri such that R1 through Rm, the rates, enable omniscience at all the terminals in M. Now, we have to show that the secrecy condition, once omniscience is obtained, then the value of the function can be computed. So it remains to show that the communication is such that the computation was secure, which means we have to show that the mutual information between the communication F1 through Fm from the various terminals is independent of Gn or nearly independent of Gn. Now we first observe that this joint mutual information can be written as the sum of these mutual informations between Fi on the one hand and Gn and all the remaining communication. Now the idea is to prove that with high probability this mutual information is close to zero for every terminal, and that gives the proof of secure computability. That proof is completed using a slight generalization of a balanced coloring lemma, which Imre talked about, was in Ahlswede and Chisar, and then a version was in the Chisar Narayan paper. And so you've heard about the balanced coloring lemma, so I don't think I need to talk about it. So from the balanced coloring lemma, it can be shown that there exist random variables F1 through Fm, one corresponding to communication from each terminal, which enable all the terminals to become omniscient, and the communication is such that it is simultaneously independent of the value of the function Gn. And this can be done if the entropy of the function G to be computed is strictly smaller than the secret key capacity. There is another question to ask, which has to do with the decomposition. We've seen that if the entropy of the key is less than the secret key capacity, then the function G can be securely computable. And therefore, it raises two natural questions. If I look at the residue, which is the value of the secret key capacity minus the entropy of the function, does it possess any operational significance? Another way of looking at this question is, can we first compute a function G securely under this condition? And can we augment it to form a secret key of optimum rate C of M? And the answer to both these questions is yes. And that answer leads to a decomposition of the total joint entropy in the system can be decomposed into the minimum rate of communication for omniscience and the largest secret key rate, namely the secrecy capacity, which in turn can be decomposed into the entropy of the function to be computed and another part which is independent of it. So the idea here is that you can take the total common randomness in the model, which is the joint entropy of all the random variables, and decompose it into three parts that are mutually independent of each each of which has an operational significance. The first part is the minimum rate of communication for omniscience. The second is the entropy of the securely computed function. And the third is a part which is independent of the other two, which when augmented to the securely computed function leads to a secret key of optimum rate. So I'll close with this general model just by saying what it is. Now suppose you have the M terminals and there is a subset A of terminals, 1 through little a, let's say. And in this model, not all the terminals wish to securely compute the function G, but only this subset A wishes to. The remaining terminals help. So clearly this is a generalization of the previous problem, because when this set A equal to M, we recover the original problem. So we want the function to be securely computed by all the terminals 1 through A. And the question is, which functions are securely computable in this way? And the answer to this question is the following. Function is securely computable if and only if its entropy now is less than the capacity of a new secrecy generation model, which we term the aided secrecy secret key generation model, in which the value of the function G is given as side information to the terminals outside the set A, which can be used only for decoding purposes but not for communication purposes. So Himanshu Tyagi will present this general result next week at the Information Theory Symposium in St. Petersburg. With that, I thank you.
Questions?
Yes.
What if the public communication in these models were anonymous? So perhaps each of the parties could make a public message, but it's not clear from whom the message comes.
So I don't know the answer to that question. Therefore, and the purpose of the public communication would be to help, but without an identity addressed to it. That's what you attach to it. Yes.
You might be able to do something with less communication, or with where you couldn't do it at all.
So I don't know what happens under this model. I don't know. I must think about this. Yeah. Thank you. Yeah.
Thank you again.
Thank you.